Hello, Luke. Welcome to lesson 93. So, today we'll be talking about two things that are actually pretty related. We're going to be talking about the products of rational expressions and the quotients of rational expressions. And essentially, we're just looking at a little bit more complicated rational expression problems here. So, dealing with multiplication and division. So let's go ahead and get started. Let's take a look at this problem here. Here we have a big, nasty multiplication problem, right? All right, we have all kinds of terms here. Notice there are sums in the numerators and in the denominators. That always makes things more complicated. And if I asked you to multiply this, what would you do? Well, you might say, well, I suppose I would multiply the numerators by each other, right? Take these two and multiply them out. And if you do that, you're going to have to use FOIL, right? Because these are sums. So you'd have to take the x squared times the x squared and go through that whole FOIL process. In the denominator, it's even more tricky because we have a sum here, and then we have a trinomial here. So we have a binomial being multiplied by a trinomial, which really gets messy. We can't use FOIL on this because it's not two binomials. And essentially what we'd have to do is take the x squared and multiply it by every term inside this set of parentheses, and then multiply the negative 7x by every term as well inside the parentheses. Okay, so big, nasty product here. And actually, if I just pull this aside, boom, that's what we'd end up with right there. So we'd end up with this big nasty numerator after we FOILed things out, and in the denominator, we'd end up with this nasty denominator. Okay? Now, this expression, it may not be obvious at first, but there's actually some simplifications that could be done in this expression. You might say it's not reduced the way that it is. And if you look closely, maybe you could recognize that all the terms have an x variable in them. And since all the terms in the numerator and denominator have an x term, we could essentially cancel out one x term out of both numerator and denominator. So that's one thing that could be done. However, even then, it wouldn't be fully reduced. And it wouldn't be obvious that it wasn't fully reduced. So we have to look and see if there's a better approach here. I'm only going through this to kind of show you what a headache this becomes when we have all of these sums being multiplied by each other in these rational expressions. Okay? So let's look at a different way of approaching this. And the thing we're going to do is actually begin, it may seem a little counterintuitive, but we're going to begin by factoring everything that we can in all of the numerators and denominators before we multiply. So let's take a look at this first numerator. We have x squared minus 25. Let's factor that. If we look at that closely, we see that that is a perfect square. So we can use the difference of two squares theorem here and say that this is going to be equal to x minus 5 times x plus 5. Right? Remember your difference of two squares. All right, so there, we factored that one as far as it could go. Now let's factor, if we can, the denominator here. Can we factor out anything here? Well, if we look closely, we could factor out an x, right? Both terms have an x in them. So we'll factor an x out, and that's going to leave us with an x on the inside minus a 7 on the inside. Okay? And at this point, it looks like I'm actually making the problem more complicated, right? Because now I've got more multiplication being done. I still have these sums to deal with. In a way, it almost looks messier now than it did before. However, let's keep going and see what happens. So if we multiply this by the next rational expression here, and we'll do the same thing. Let's take the numerator here and we'll factor it. What happens? Well, we can factor out an x. And if we factor out an x, we're left with, on the inside here, a single x plus 3. Right? Okay? And then if we look at our denominator, we could factor out our denominator. And in this case, we're kind of doing the opposite of the FOIL here. So we have the x, we're going to have a minus and a plus. we're going to have, let's see, a 15 would be a 3 and a 5 to get me to a 2. So the 5 goes with the negative, 5 and 3, and there we go. All right, so now at this point, this is where the magic happens. And honestly, this is really where we see that these problems are a bit contrived. In the real world, problems aren't going to work out as nicely as this, but the goal is to just try to show you an approach to take to try to make reducing a little bit easier. It's not always going to work, but in these problems, it does. And it's because these problems are contrived. So anyway, just a little bit of a warning there. In real life, it's not so nice. But anyway, let's take a look at this. What can we do? Well, we can now reduce out some things. Okay, what could we reduce out? Well, right here, right? This top term, this numerator, is you might think of it as being multiplied. It's two factors being multiplied by each other, an x times an x plus 3. And down here we have two factors being multiplied by each other. It's an x minus 5 times an x plus 3. Notice we have an x plus 3 that's a factor for both the numerator and the denominator. Well, that can actually just reduce itself out. X plus 3 divided by x plus 3 is just going to be a 1. So it just reduces itself out. And boom, that part is gone. Okay? In like manner, think about how we can reduce. I'm just going to put an example over here to just remind you of the process. If I have, 3/9, let's say, and I'm multiplying that by, I don't know, maybe 12, 24ths, okay? We can recognize that this 3 can go into itself once, and this 3 can go into the 24 8 times, right? We're cross-canceling here. Remember that? Okay, and then we could say, all right, a 3 can go into a 9 3 times, a 3 can go into a 12 4 times, right? It's just a way of reducing. And then we can, so not only can we go kind of crosswise, cross-canceling, but then we can also say, okay, 4 over 8. Well, we can kind of go, again, from the numerator to the denominator. 4 can go into itself once, it can go into an 8 twice, right? So we're doing all this canceling out. We can do it by either cross-canceling or canceling something in the numerator and in the denominator. Okay, so kind of remembering this process, we're doing the same thing here, only we have kind of expressions here and variables instead of just numbers. So we crossed out the x plus 3. Let's look for cross-canceling. Can we do any cross-canceling? And the answer is yes. We have an x here. This could cross-cancel with this x over here, right? And we have an x minus 5 here, which can cross-cancel with this x minus 5. Isn't that beautiful? Look at that. We just lost this whole expression over here. It's now a 1 over a 1. And this expression times that is just going to be this expression. So what are we left with? Well, we're left with simply an x plus 5 over, and I'm getting that from right here. I'm not multiplying that by anything anymore. It's all been canceled out. Over an x minus 7. And again, that isn't multiplied by anything because it's all been canceled out. So we end up with x plus 5 over x minus 7. That is the reduced product for this problem. Okay. Now compare this to this. Vastly different, right? It would be kind of hard to believe just based on looking at this one that this could be reduced down to this. Okay. It's a big difference between those two. And that's why sometimes it's nice to factor things as much as we can first before we multiply, particularly in rational expressions. Okay? All right, so let's take what we've learned now and try it with a problem. So go ahead and try this one on your own. Pause the video, and then we'll do it together. All right, so let's see how you did. We're going to take the numerator, and we will factor it. So this is going to be, again, kind of the opposite of the FOIL here. We have our two parentheses. We have an x and an x. The minus means they're different signs, so we have a minus and a plus. And then we have to think of what two factors of a 6 could somehow work out to give me a 1. Well, it'd be a 3 and a 2, right? And the 3 is going to go with the positive sign because it's the larger number. All right, so there we go. That's what we end up with that, or for the numerator. In the denominator, we have, again, our set of parentheses. So we have an x, we have an x. It's going to be a minus and a plus. 21, it's going to be a 7 and a 3, right? 7 and a 3 would get me to that 4. 7's going to have the negative. And there we go. All right, then we're multiplying that by the next numerator, which again is a set of parentheses. So we have an x and an x. It's going to be the same sign, and it's going to be a 7 and a 1. All right. And then we have in the denominator an x and an x. It's going to be a 2 and a 1, and it's going to be a negative and a positive. 2 is going to go here. 1 is going to go over here. All right. So there we go. We have all of our expressions factored. Now let's do some cross-canceling. This is the fun part. This is where we get to reduce things out. So x plus 3 and an x plus 3, they're going to eliminate each other. An x minus 7 is going to eliminate this x minus 7. This x minus 2 is going to eliminate this x minus 2. And look at that. Isn't that beautiful? We end up with x minus 1 over x plus 1. There we are. Okay? Very good. All right, now we're going to switch gears just a little bit here. We're going to talk about division of two nasty rational expressions. Okay? And it's going to be the same process. We're going to employ factoring here to try to make things a little bit easier. But there's just one step that we need to do first. And when we have division set up like this, we need to recall that back in the day in grade school, when we had things like 1/2 divided by 1/4, what did we do? Do you recall? Remember, we took the 1/2, we multiplied it by the reciprocal of the second number. So the reciprocal of 1/4 is 4 over 1. Okay? That's how we did this kind of division of rational expressions. Then, of course, we can reduce, cross-reduce here, cross-cancel, and we end up with 2 is our answer. But the important thing is remembering that when we're dividing two fractions, we flip, we find the reciprocal of the second fraction, and we multiply the two together. That's the same process we're going to use here. Okay? And so it's very simple. We're just simply going to rewrite this problem as x squared. And you know what? Maybe to save time, let's factor this first. So we'll factor this top numerator here. So x squared minus 2x. What can we factor? Well, we can factor out an x, right? Both terms have an x. So it's going to be x times x minus 2. And then in the denominator, we're going to have our double set of parentheses. So we have an x, an 8. Well, let's see, our sign is a negative sign, so we're going to have opposite signs. An 8, let's see, the factors for an 8 to give me a 2 would be a 4 and a 2. 4 is going to go with the positive number, or positive sign. There we go. And now, this we're going to write as a multiplication sign, and we're going to flip this. We're going to take the reciprocal of it, which is x squared plus 7x plus 12 all over x squared plus 5x. Okay? We use the same method that we used up here. Okay? We just flip that second expression, that second rational expression. And then once we've flipped it, now we can go ahead and find, or factor this out as well. So maybe I'll just rewrite the first one here. We have x minus 2 over x minus 2x plus 4. And then we're multiplying that by, in the numerator, we're going to have our set of parentheses here. And it's going to be x. A 12 would be 4 and 3. It's going to have the same sign, positive sign. 4 and 3. All right. And then in the denominator, we can factor out an x. That's going to give us x times x plus 5. Okay. So there we go. Now at this point, again, this is the fun part. This is where we get to cross things out. So what can we do? Well, the x minus 2 can eliminate the x minus 2. We can cross-cancel the x and the x, cross-cancel the x plus 4 and the x plus 4, and we're left with x plus 3 over x plus 5. There we are. There would be our answer. Okay? Excellent. Let's try one more to make sure you've got it. So go ahead and try this one on your own, and then we will do it together. All right, so let's see how you did. So in the first expression, we'll take the numerator and factor it. And we're going to have an x and an x, different signs, 3 and 2. Denominator will have, again, 2 parentheses. We're going to have an x and an x. And let's see here. What would give us a 10? 5 and 2. 5 is going to have a negative sign. 2 would be over here. All right. And then we're going to multiply. Now I'm just going to take this denominator and put it on top, but I'm going to write it by factoring it. So we're just saving ourselves a little time here. We don't have to rewrite it. So we end up with x and x. Let's see. Let's see. 20 would be 5 and 4. So we have a negative and a positive. 5 goes here. 4 goes here. Okay. And then in the denominator, which is actually the numerator up here, we're going to have another set of parentheses, and this will be an x and an x. It's going to be a 4 and a 1 and a plus and a plus. Okay? And then we can start canceling out. We get these two to go away. We get the x minus 5s to go away. We get the x plus 4s to go away. And we're left with an x minus 3 over an x plus 1. And there is our solution. All right? Very good. So this should be a pretty straightforward and really, I think, easy lesson. We're just reviewing some different concepts. We're kind of putting some things together. And it's kind of fun because it's not a lot of work, and yet we get to see all of this stuff disappear, and it just becomes so nice and simple. If only it worked that way in real life all the time, which it doesn't. But it's fun while it lasts, while they've contrived these problems to turn out this easy. Okay, very good. Well, we will stop here, and I will see you tomorrow.